very important topic. Yeah, Laplace transform. Yeah. First, I need to spend some time to explain why this method is a good one, powerful, important method solving ODE. Yeah. C.1, basic properties of Laplace transform. Yeah. First, I want to, look at the big picture. So why we need a Laplace transform? So this transform method, so this Laplace is one of the transform method. In problem solving, there is a special method called a transform-based method. So the idea is quite different from, our usual problem solving methods. The transform method. All right. How different? The key motivation for learning about is that, so let's look at this, the process of solving an ODE. Is simplified to an algebraic problem. All right. So here. So look at the whole process. How do we use this Laplace transform method to solve an ODE? First, we are given an initial value problem, IVP. After that, then we do not use our normal method. So here we use a completely new method. We do conversion. Because this is a differential equation, ODE, right? Differential equation. We know usually differential equation is harder to solve than algebraic equations. Algebraic equations, we know, because we do not need to worry about derivative, integral. So, multiplication, division, those things much easier to work on. If you need to consider derivative, second derivative, integrals, then it's much harder. So if you have some way to help you convert from ODE to some algebraic problem. That means this new problem does not contain any derivative, any integral, just plain algebraic equations. Then it becomes much easier to solve. So then you only need to solve that algebraic problem. After that, you need to go back, because your goal is find a solution of the original ODE. And here you change the problem. So you need to go back to the original problem. So you need some inverse transform. So this place you need a transform, and here you need the inverse transform. Going back to the original form, the original representation. So then, after the inverse, you get a solution of the IVP. So that approach, so that the high level understanding. So here, this is the typical transform-based method. So remember, you may heard of Fourier transform, right? So later, after the midterm, we will learn the Fourier transform. Yeah, the similar idea. Yeah, so usually here, let me describe the general transform-based method. Yeah, why people, many times people like to use the transform-based method. Yeah, it is very effective. So you have some type of normal problems, yeah, in certain domain. Yeah, so here, yeah, so there is the concept. Because when you talk about some problem, the problem usually there is some domain you consider. Okay, yeah. So here the domain is, so although in our textbook people do not use this domain, yeah, but here I talk about the general transform problem, not just for the Laplace transform, the general, yeah, many different kinds of transform based method. So usually, yeah, the original problem works in certain domain. Okay, yeah. So here you can understand, this ODE domain, right? Yeah, ODE because domain you can understand as some environment, right? So domain, some suitable environment. Yeah, that's the meaning of this domain. Yeah. So here we use the ODE environment domain. That means in this environment, you need to work on derivatives, integrals, and related operations. Yeah. So that's one domain. Yeah. But in this domain, when you solve a problem that's not easy, pretty hard, yeah, then you want to change to a different domain. Okay, yeah. So the transform method helps you go to a different domain. Okay, yeah. So you change the domain by a transform. Okay, yeah. So here in this particular case, we change to algebraic domain. How about that? Okay, algebraic equation. That environment, right? So here you can understand it's a different environment. In this new environment, you do not need to worry about derivatives, integrals, everything about algebra. Okay, yeah. Algebraic operations. Yeah. Yeah. So that idea. Yeah. But after you find a solution in a new domain, yeah. So here, we assume some new domain. Okay. So you do the problem solving in a new domain. Okay. Yeah. But after you get a solution, you need to go back to the old domain. Okay. Old domain by the inverse transform. So this by, yeah, so by a transform here. So here, by its inverse transform. Every transform must have an inverse transform. Otherwise, it's useless. Okay? Yeah. When you talk about some transform, any transform must have its corresponding inverse transform. Otherwise, this method is useless. Okay? Yeah. So our Laplace transform, we have inverse Laplace transform. Fourier transform, we have inverse Fourier transform. Yeah. Otherwise, not useless. Yeah. So you transform it to a different domain, then you cannot come back. Okay. If you do not have the inverse transform, you can never come back. Yeah. All right. So that's the general picture. Yeah. All right. This type of mathematics, let me erase this. Yeah, converts problem of calculus. Yeah, when you use derivative, integral, that's the problem of calculus to algebraic problem. Yeah, is known as operational calculus. Yeah, just some name. Okay. Yeah. All right. The main advantages here. Let's look at the properties. Yeah. So the main advantages of this method. Yeah. The problems are solved more directly. Yeah. Initial value problems are solved without first determining a general solution. Yeah, because you apply the transform. When you apply the transform, the Laplace transform covers both the equation part and the initial value part together. Yeah. Later, we will have some formula. Okay, so the formula, in our formula, we combine the initial value condition and the equation part together. Okay, yeah. So you do not need to, work on the general solution first, then you plug in that initial condition to get a particular solution. So that's our old way. Okay, our old way. Yeah. Although we haven't practiced, we learned that method, but we need to do some practice using our older method. Yeah. And then this method, so you work on the whole thing together. Okay, yeah. That's one property. The non-homogeneous, when you solve non-homogeneous ODE, you can apply the Laplace transform on the whole equation directly. You do not need to split into two steps. First, working on homogeneous, and the second, then you go to the non-homogeneous. That's our older way, right? So you separate in two steps. Yeah. But Laplace transform, so you do not split. You work on the non-homogeneous ODE directly. Okay? Yeah. So that's another advantage. Yeah. All right. Then this circle number 2, another important advantage. Yeah. The method is particularly powerful for problems with inputs. Yeah. Input function, the inputs that have discontinuities. Yes. So what's that input? Here, let me remind you, when we learned that first order ODE, we consider this special equation y prime plus p of x times y equals r of x. In that system, we call this r of x as the input. Okay, as the input. Yeah. Here we can generalize to second order, right? Yeah. Y double prime plus p of x times y prime plus q of x times y equals r of x. Yeah. And in this case, this is the input. Okay, our function input. Then here it talks about the input that have discontinuities. Discontinuities. Okay. Yeah. So if we draw graph, draw graph, the r function r of x, it can contain discontinuity, like curve like that. Discontinuity like this. Okay, the r function, so here I should remove that, starting from this point. Okay, so here this is discontinuity. Okay, even r function contains several discontinuity points, so this Laplace transform method still can make it work. Okay. Here you can see our old method. It's hard, right? Our old method a little hard. Yeah. But you don't worry, with discontinuity, you can still take integral, right? Yeah, you can still take integral. Yeah. Yeah. But you will, when you work, it becomes much harder, okay, with discontinuity. So that's a, this method. Yeah. Another important advantage. Yeah. All right. Here, two examples. Heaviside function. One important discontinuous function we call Heaviside function. So what's that Heaviside function? So this is xy coordinate system. All right. Then you draw a function, step function. Yeah, the Heaviside function is, when x less than 0, it is 0. Okay, when at the positive side, it's 1, constant 1. Okay, this is a Heaviside function. Okay, so 0, then you have discontinuity. You jump to 1 after 0. Okay, before 0, it's 0. After 0, it is 1. So that is the Heaviside function. Okay, yeah. So this function looks very simple, yeah, but very useful. Yeah. Later you will see in Laplace transform. Yeah, so this function is very, very useful. Yeah. All right. The first. Second, Dirac's delta function. Another very special, very important function called Dirac's delta function. All right. Yeah. How special it is. Yeah, so here. Dirac's delta function. Here. Yeah. All right. Yeah. XY coordinate. Dirac's delta function. So this function actually it's so special. So 0, 0, okay, 0, 0, jump, okay, all right. 0, 0, yeah. So there is a peak, the peak, very high peak, okay. But this narrow, skinny peak covers some area, okay. So this area is 1. Area is 1. Yeah. Then, very skinny, okay. Yeah. That's the Dirac's delta function, delta of x. So this function also very important in our Laplace transform method. Yeah. Yeah. Actually, you can see when you take a derivative of the Heaviside function, okay, you take a derivative of Heaviside function, okay, you get a delta function. Derivative of that delta function. Yeah. Actually, delta function is not a regular function. Yeah. So, because based on the function definition, we cannot call delta function as a function. It's not a function. Our function, there is a definition, right? Yeah, but its behavior, this kind of special behavior, it does not follow the definition of a normal function. So that's why sometimes people call it generalized function. It's not a normal function. Okay? Sometimes one name is the generalized function. Another name is people call distribution. Yeah. It's not a function, it's a distribution. Okay? Distribution is another concept, different from the function concept. Okay? Yeah. And the distribution actually the same meaning as the generalized function. Just different people call it in different name. Yeah. All right. Yeah, so that's the, this slide. Yeah, to give you some background information. Yeah. Next, definition of Laplace transform. Now we need to write the formula. Yeah. So, what is the Laplace transform? Yeah. Yeah. The formula is like this. Yeah. Integral. Okay, yeah. First, here we use capital F of S, this, curved L, okay? Yeah, it's a L, Laplace L, yeah, but, the textbook, the author used this, curved way to write L, yeah, L of F, yeah. Then, integral from 0 to infinity, then there is a e function, e to the negative s times t. S is treated as a parameter. S is treated as a parameter. T is used as the integral dummy variable. Okay, t, yeah, because the t here is a dummy variable. Yeah. When you do the integral, you need to use that t, but after you get the integral, t is gone. Okay, yeah, yeah. So it's different from s. Yeah. S, when you take the integral, you treat s as a constant. Yeah. When you do the integral, you treat that s as a constant. Okay, all right. Yeah. So this is the definition of the Laplace transform. Yeah. And based on this definition, you can have many special properties of Laplace transform. Yeah. Yeah. All right. Yeah. Yeah. So at this point, so you may feel, why you define a transform like this? Yeah. Yeah. In math history, a lot of things, a lot of techniques, methods, concepts developed. So there is a lot of history. Okay, so many books about the math history. Yeah, so usually, it's not a bit well known. Yeah, even for mathematicians. So a lot of histories may not be known. Yeah. All right. Yeah. Kernel concept. Yeah. Here, just the terminology. Yeah. Yeah. So most people may not look at using this term kernel. Yeah. But for mathematicians, yeah. So they want to interpret the special structure, using some formal way to interpret the structure. So they introduced this kernel concept. What's that? What's the kernel? Kernel is a two-variable function. Yeah. So a kernel function usually contains two variables, s and t. Okay. Yeah. And for this one, we take this e function as the kernel. Okay. E to the negative st as the kernel function. We define our kernel function in this one. Yeah. Then, because when people introduce this kernel concept, they can use this kernel way to define many different kinds of operations. The transform, yeah. So people use the kernel way to define transform. Okay, this is the general way. You can treat this as the general way to define the transform. Okay, general way for transform. Okay, when you take a different kernel, then you jump to a different transform. Okay, so in this way you can define large number of transforms. Yeah. But the problem is, for some of the kernel functions, the transform has some very nice properties. But if you choose the kernel not very good, then the transform cannot give you any good property, just garbage properties. Yeah. But people only interested in those transforms with excellent, great properties. Yeah. So the Laplace transform, Fourier transform, so you have many, simple and, useful properties. Yeah. But if you choose the bad kernel, so you get some, garbage properties. Okay, useless. Yeah. All right. Yeah. Inverse Laplace transform. Yeah, because in order to make the Laplace transform useful, you have to find its inverse transform. Yeah. To go back from that new domain, right? Yeah. Otherwise, you cannot come back from, the working domain. Yeah. So you do your work in that new domain. Yeah. But you need to come back. Yeah. All right. So then the question, how to define inverse Laplace transform? Yeah. That is a question, right? Yeah. We really need inverse Laplace transform. The question is how to get that Laplace transform. So another question we need to answer here. Yeah. All right. So let me explain that question. First, the notation of the Laplace transform. Yeah. So for the inverse, that means you know the Laplace transform. Capital F of S. Capital F of S, that function is known. Okay? But you do not know this little f function. Yeah. Little original function. This little f function is the original function. So think about in this way. Okay? When you start, you have that little f original function. Then you apply Laplace transform on it. So you get a capital F function. All right? Yeah. Now, people hide the original function. Okay? People do not tell you that what that little f function is. Yeah. People just give you that capital F function after Laplace transform. Yeah, so this is the capital function after we apply the Laplace transform. Now, they ask you to recover the original little f function. Okay? From the capital F function, you need to recover. You need to apply inverse Laplace transform to recover the original little f function. Yeah. Here, this is a notation. Okay? Inverse Laplace transform, we use this, this inverse way. Yeah. That L sup -1. Yeah. So we represent as the inverse function. Yeah. All right. So to get a little function recover, we apply some kind of inverse Laplace transform on f. So then our goal, we want to get the little f function from capital F. Yeah. But what is the definition of this L inverse? Yeah. The definition is not clear. Okay? Or I can say it this way. Nobody can find the formula for this inverse Laplace transform. Yeah. For Fourier transform, later you will see. Fourier transform, we can easily get a formula for inverse Fourier transform. Yeah, there is a specific formula. But for Laplace transform, there is no specific formula for the inverse Laplace transform. Yeah, because people couldn't figure out. People couldn't figure out under what special operation you can get a, inverse Laplace transform. Yeah, so the definition here is it is a question mark. Yeah. But yeah, it can be shown that inverse transform exists. Yeah. Although people couldn't write out its formula, okay, but it exists. It's there. Yeah, the inverse transform exists. Okay, it has no specific representation, but it exists. Okay, all right. Then the inverse transform can be found from Laplace transform. Yeah. Because inverse transform just the opposite way, right? Yeah. So how do we get inverse transform? We get inverse transform from the original Laplace transform. If we can get Laplace transform, we just take the same formula and we go the inverse way. We go the opposite way, okay? Opposite way, yeah. The result, we treat the result as the input, right? We treat the input as the output. We switch the input and the output. Then we get an inverse Laplace transform, yeah? So we can get the results of the inverse Laplace transform, but we do not have the formula representation for inverse Laplace transform. Yeah. So that's the situation. Okay. Yeah. All right. Yeah. And the inverse transform should have the property, if you combine it with the original Laplace transform in these two different ways. Yeah. Yeah. So you first apply Laplace transform. Yeah. So because this is the first, you first apply Laplace transform on f. After that, you apply inverse Laplace transform on the result. You go back to the original function. Yeah. Here is, you apply inverse transform on capital F. Yeah. First, you apply inverse transform on capital F. Second, then you apply Laplace transform on the result. So you get F. Yeah. So that's the basic properties for the inverse transform. For any inverse transform, you can have these two similar properties. Yeah. Any inverse transform. Okay. Otherwise, it won't be an inverse transform. Okay. Yeah. If these two properties, two identities are not satisfied, we won't call it inverse transform. Yeah. All right. Then linearity of Laplace transform. Yeah. Because Laplace transform, we use integral to define Laplace transform. Integral operation has the linearity property, right? Yeah. Derivative operation has the linearity property, and integral operation also has the linearity property. Okay, yeah. So that's Laplace transform inherits the linearity property from the integral. Yeah. Yeah. So that specifically, you have two functions, f function, g function. You work on the linear combination of these two functions. Yeah. A times f function plus b times g function. A, b both constant. Yeah. So you can use the the simple linearity property. Yeah. Yeah. In this way, yeah, so you only need to know the formulas for some basic functions. Yeah, because later when you combine several basic functions using the linear combination way, yeah, then you apply the linearity property. Yeah, so you can find the Laplace transform. Yeah. All right. Then Laplace transforms of simple functions. Yeah. The basic formulas. Yeah. So we need a set of basic formulas. Yeah. When we have this set of basic formulas, later when we have more complicated functions, we can use the linearity property from the previous slide to, write the Laplace transform of a complex function as a linear combination of several Laplace transform of the basic functions. Yeah. So that way, yeah. All right, so let's look at some basic formula. The first one, we apply Laplace transform on constant 1. Okay, yeah. That's a very simple case we need. Yeah. Yeah. Because if you know this L of 1, then L of 2, F of 100, you can get easily, right? By the linearity property. L of 100, you just take 100 out. Yeah. by the linearity property, you take 100 out. Yeah. All right, so you need to find this L of 1 first. Yeah. And we use the definition here. I put the definition of Laplace transform here. Okay. All right. So we can calculate the 1. Little f function is 1. Little f function is 1. So you only have that e function part. Yeah. Then integral by parts. Yeah. Integral by parts, right? Yeah. But at infinity, you need to take limit. Yeah. Yeah, because you can plug in 0, but when you plug in that infinity, you need to take the limit. Okay? Yeah. All right. So then, yeah. Then, actually here we do not need integral by parts because we can find the integral, right? Yeah. So here we can find its integral. Yeah. Then we, evaluate at the 2 points, but at infinity, you need to use the limit. Okay. You need to use that when t approaches infinity, that e function becomes 0. Remember, s here, here s is positive. Yeah. Here s is positive. Yeah. Otherwise, when t goes to infinity, it won't be 0. The e term. So here s is positive. Yeah. All right. Yeah. If s is not positive, then this formula does not work. Yeah. Yeah. All right. Yeah. So here I put that condition, positive. Yeah. All right. Second formula. This time we apply Laplace transform on e function. Another basic formula, e to the constant a times t. Yeah. Then we plug in that formula. Yeah, both e functions, so you can combine, right? Parenthesis s minus a. Yeah. Then you can get 1 over s minus a. Okay. Yeah. Still, yeah. This integral you can find easily. Okay. And you take limit. At infinity, you take limit, but you need a condition s greater than a. Otherwise, you won't get this formula. Okay. Yeah, s must be greater than a. The third one, this time, hyperbolic. So look at this function. We call it hyperbolic function. Okay. Yeah. So in calculus, so you learn this hyperbolic function. So it's not cosine. Yeah. Yeah. But the hyperbolic cosine function. Okay. Now. Yeah. The definition is this. Yeah. The hyperbolic cosine h of x. E to the x plus e to the negative x. Okay? Yeah. Yeah. The cosine, yeah. So here you compare it with our regular cosine x. Okay? E to the ix. Okay? Yeah. That, imaginary unit I, e to the negative ix. So you can see the difference. Yeah. The difference is we remove that I here. Okay. Yeah. Hyperbolic cosine function here. By linearity, yeah, because that you have 1/2, you have, 2 terms, you plus apply the linearity principle, you can split in this way. Yeah. And each term you can apply the formula number 2. Yeah, so you can find its Laplace transform in this way. Okay, so that's the hyperbolic cosine function. Similarly, hyperbolic sine function. Yeah, sine function. You just change, plus to minus. Okay, sine hyperbolic x e to the x minus e to the negative x over 2. So you apply the linearity property, yeah, simplification. So you get a, hyperbolic Laplace transform of hyperbolic sine function. Yeah. All right. Then cosine function. Yeah, cosine function. The constant we use omega here. Okay. Yeah. Then this one a little hard to find. Yeah, this for cosine. Yeah, harder than the hyperbolic functions. Yeah. Yeah. When we calculate this one, we need to calculate together with Laplace transform of sine function. Yeah. As a pair. Yeah. We need to, yeah. So because the calculation, the two functions are involved each other. Yeah. So we need to, work on these two functions together. So we introduce a notation L sub C, yeah, as the result of the Laplace transform of the cosine omega x. Okay. Then number 6, the sine version, we use a L sub S. Yeah. Yeah. Because when we do the integration by parts, these two expressions are involved each other. Okay. So we need to find a solution from two expressions. Okay. So here we have two notations, and we need to find expressions together. Okay. All right. So that integration by parts, yeah, because we from working on the definition, yeah, plug in. So this, integration by parts, yeah. So you get this expression, but this expression LS is used, okay, yeah. But the LS at this point is unknown, right? Yeah. Yeah. So let's do the integration by parts on the second one, yeah. Second one, this LC is used, okay, yeah. But we combine these two equations, okay. So we can get LC equals, yeah, this expression, LS equals another expression, okay, yeah. So in this way, we can find Laplace transforms form of these two functions, okay? Sine, cosine, yeah, also very useful. Okay. All right, yeah. So the last one here in this slide, the last one, calculate Laplace transform on this power function. You can call power function. Yeah, but this power function, our n is expected to be, yeah. Is it necessary to be integer? N plus 1. Yeah. Yeah, n plus 1. Yeah. Yeah. Yeah, but actually it is. Yeah. Actually, we need this n as an integer. Yeah. All right. So here you still, so you do the integration by parts like that. Okay. Yeah. And when you plug in two limits, two integral limits, it's gone. Okay. Yeah. You take t approaches infinity. Yeah. Plug in 0, it's 0. Infinity also 0. Yeah. Because E function decreases much faster than than that power function. Okay, yeah. So eventually, it becomes 0. Yeah. So the first term becomes 0. So you only have the second term. But second term, this is a Laplace transform of this t to the n. Okay, yeah. So you get this property. Yeah, Laplace transform of t to the n plus 1 equals, yeah, you know, like that. But you can do iterations. Yeah. So at the end, you get this n plus 1 factorial over s to the n plus 2. Yeah. So you need that n must be integer. Okay. Yeah. And n must be non-negative integer, right? Yeah. And you can take 0. And you can take 0. Yeah. 0, 1, 2. So non-negative integer. Okay. Yeah. If negative 1, if n is negative 1, you get our first basic formula, right? Yeah. T to the 0, that's 1. Yeah. So so in this formula we consider n greater or equal to 0. Yeah. All right. Yeah. And now you can see with these formulas, although there are many more formulas, but these basic formula most commonly used Laplace transforms. Yeah. So we can solve large number of ODE problem. Yeah. All right. And so here, I think, yeah, we will run out of time soon. Yeah. So, yeah, let me just say something about this slide. Because with the time remaining a few minutes, we cannot start a new slide. Yeah, let me just say some final comments about this slide. Yeah. So then we finish our introduction. The first view of Laplace transform. Yeah. All right. Remember, I talked about in the previous slide. I talked about the inverse Laplace transform. There is no specific formula, right? Yeah. Yeah, because nobody can find this concrete formula for the inverse Laplace transform. Yeah, yeah. But it does not prevent us. It does not prevent us from applying inverse Laplace transform. Yeah, we have a way to figure out the inverse Laplace transform. Yeah. For example, so here we have 7 formulas, right? Yeah, this slide, we have 7 basic Laplace transform formulas. Yeah. Then, based on the understanding of the inverse Laplace transform, we just, for each formula, we just work in the opposite way. So we can get the inverse formula immediately, right? So, inverse of this 1 over s equals 1. How about that? Okay. Yeah. So you just switch input output, right? Yeah. So you, based on the Laplace transform formula, yeah. So you swap that inverse, input and output. So you get the inverse formula. Okay. For this one, so you inverse Laplace transform 1 over that s minus a, then e to the at. How about that? Okay, pretty easy, right? Yeah. So here you can see, whenever you have a Laplace transform formula, you can write its inverse formula, corresponding inverse formula version immediately. Yeah. Just swapping the input and output. Okay? So that's so simple. But you cannot use the specific formula to write the definition of the inverse Laplace formula. Yeah, yeah. But it exists. Yeah, first. Yeah, later we will have a theorem to show. So under what condition? Yeah, you know, the Laplace transform, inverse transform exists. Then you just check those conditions. Under those conditions, you know, Laplace transform, inverse transform both exists. Then, so you just apply these formulas. Okay? Yeah. Yeah. All right. So that's all we have for our first Laplace transform class. Yeah. So later we will, you know, study many more properties, and we will use it to solve ODEs. Yeah. All right, that's it. So then I stay a few more